Hello, we are Team 29. Our project is to convert 2D images into a 3D model, and our client is Avanade. Technological progress and the outbreak of the pandemic increased the demand for remote meetings on VR. With the development of Microsoft Mesh and VR techniques, user-created content will be pivotal. Traditionally, 3D modeling requires professional skills, done with specialist software. This will hurt the popularization of VR, as it is inaccessible for the majority of users. We want to make the process of 3D modeling to be simple and accessible to users with little or no experience. Based on the background and the problem, there are three key requirements to our project. Research techniques to convert 2D images into 3D models, evaluate the techniques, and create a proof of concept tool.
We researched 7 deep learning solutions that use various techniques to convert 2D images to 3D models. We also had a hardware-based solution that involved using a LiDAR sensor on the Azure Connect camera. We chose 2 techniques, DenseDep and 3D R2N2, to further test and evaluate. We wanted to create a demo showcasing how a user would be able to convert a 2D image to 3D model. We chose DenseDep for 3D object generation. The basic toolchain model is to first get the source code of DenseDep, compile it into an executable using PyInstaller. We then connect the executable to a GUI so that a user can run DenseDep in a user-friendly environment. For the GUI, we use the model view controller design pattern. We developed the GUI in Python with PyQt5 and Open3D to visualize the 3D models files generated by DenseDep. Here's a demonstration of our GUI.
The last component of our project is a report outlining all our findings from our research. So this includes summarizing each solution and evaluation of each one using both our own tests and existing research. So for testing, I've created an extendable framework where solutions are passed into various test objects. The test data is from the ShapeNet database, which is a database of images of objects from different angles and their ground truth 3D models. So as a summary of some of our report's findings, I have compared our 2 main solutions. You can see here that DenseDep is significantly faster on average on like a regular computer, one of the reasons why it was chosen to be implemented in our demo tool. So comparing the performance of these 2 solutions directly is not possible since they have different outputs. So they have different ways of measuring the success of the modeling. So instead, they are evaluated against other similar solutions. So DenseDep, a loss function can be defined by comparing the generated map against a ground truth, in particular comparing the depth values and the depth gradient. And we see the average error for DenseDep is lower or comparable to other solutions. For 3D R2N2, it can be single or multi-view, and we see that the IOU generally improves with the number of images input, meaning that for a user, this means if they can take multiple photos of the same object, they can get a better 3D reconstruction with this method. And 3D R2N2 is also compared against other solutions across multiple image categories. On average, performing better, though there are some edge cases, such as like a chair with thin legs and a computer monitor. So these will be solved, as the technology improves over time. So overall, we have compared our 2D to 3D solutions, created a testing framework, created a demo, and summarized our findings in a report. So here now are our references, and thank you for watching.